I'm going to record this so that we can have a track, right? I'm going to share my screen again so that we can all see what, it's the same thing that we're all seeing. We're just going to go, so I guess we could go room by room, and you can show us for each room like what you found. Like, are there patterns that you're seeing? Are you seeing discrepancies? People who are not presenting, I want you to really pay attention to what are you seeing and what are you not seeing on the board. So like, if it was your board and you want to make this like the perfect board, if this was your data and you want to make this the perfect data, what is possibly could be added to their data that may be missing on this point, but like maybe you would like to see happen. Okay, so let's go. Room 1. That's Zach, Ian, and Layla.
I guess I can start. So for our observations, you can see 2 of our graphs down here. We thought that the data looks pretty similar overall. Like, we made sure to drop it from roughly the same height, just under 2 meters, I think. And then it seems to fall pretty linearly, because you can see on the graph. But my data, I have more dots than Ian's. So that might be why his data looks slightly more linear than mine does, but overall it's pretty straight.
Okay.
And we think that it's linear because with like the high drag and the low weight of the filters, the filter, when we drop the filters, that they'd reach terminal velocity pretty fast.
Okay. Did you all drop the same number of filters?
Yeah.
Okay, and you dropped it just about the same height?
We dropped it like 5 feet.
Dropped it from about 5 feet. Okay, and did they all take the same amount of time to fall down?
We did not discuss that part. We should have brought that
I
up.
mean, like, no, but I mean, like, do that? Look at your data.
Not really.
Okay, so that's something that you want to think about, right? Like, if you have the same number of coffee filters falling from the same height, what, you know, are they in fact falling at the same rate or not, right? Okay, so anything else on room 1? We'll switch to room 2 and then we'll come back and have a sort of meta conversation. Okay, so room 2, that would be Jordan, Ruby, and Ronan.
Okay, so for the patterns, the coffee filters seem to speed up and hit, then hit constant velocity. And then Ruby, for inconsistencies, Ruby used a different type of coffee filters than we use, and we all kind of dropped it from different heights.
Okay.
But our whole group used 5 coffee filters, and it weighs 0.125 of a Newton. And we learned that the Vineyard data tells us that the coffee filters are falling at a constant velocity.
I thought they were speeding up first.
Yeah. Oh, I forgot to add that, but.
Well, no, that's what you said at the beginning, right? Coffee filters seem to speed up and then hit a constant velocity. So you want to revise your last statement, or I don't know. The rest of the group, Ruby, Ronan, what do you have to say?
Yeah, we just forgot to repeat that it's sped up at the beginning for the last part.
Okay. How do you know that it's sped up at the beginning?
When we looked at our graphs, we can see that the at the beginning of just I'm looking at my graph right now. You can see that the curve, it starts pretty like slow, balanced, almost straight, and then it curves downwards, and then at a certain point, about like a third of the way through, it's falling at like a consistent slant.
So like
yeah, it speeds up more towards like the middle. Like it's like slower at the beginning and then it speeds up in the middle.
Okay.
Yeah.
Okay. So slow at the beginning, right? And then speeding up by getting steeper, right? Less steep, more steep. This one actually looks like it's the same. I don't know. Interesting. Okay, cool. That's room 2. Notice a lot of different units, right? Some of you are in inches, some of you are in feet. Previous group was in meters. Okay, room 3. Ollie, Reed, and Casper.
All right. So for our group, so just to start off, Reed accidentally dropped one filter at a time, so we don't have his data.
Yeah. Okay. So I wasn't here when you explained the how to record the data or what the CP project. Anyways, but yeah, I dropped each one separately instead of all of them at the same time. So
Okay.
I'm gonna redo that.
But for me and Casper's data, it shows for the most part an increase in velocity, and I think we might have had different filters because Casper's weighed 0.1 newtons and mine weighed 0.2.
Okay, so maybe you had different Newton. You also have something that's different from the other groups. You have 2 sets of curves, right? You have like the red and the blue curve.
Mm-hmm.
You want to talk a little bit about that? Because we haven't seen in the other groups, it was all like, there was just one curve, if I remember correctly.
So ours, it might have just been like a bad trial, but it did curve a little bit going side to side on both of ours. And
Okay.
that's what the curve in the red line's for. And then the blue line is obviously like up and down.
Okay, so the blue line is up and down and the red line is side to side?
Mm-hmm. Yeah.
Okay. And you can see that in here, right? Like you can see that in your, right? You can see the thing curving back and forth.
Yeah.
Cool. So in many ways, Ollie, I'm just gonna take your data, although Casper could take your data as well, right? It speeds up, right? It gets steeper and steeper. And then it looks like it's fairly linear, like right here. Does that make sense? Right? It speeds up, gets a little bit steeper, and then it's sort of linear over here. Casper, is this your video right here?
Yes, it is.
So I want the whole class to think about this for a second. So Casper's data shows that vertically, right? Vertically, it speeds up. And then it seems like vertically, it's going down at a constant-ish, right? Like it seems like the speed is about the same. Is about constant. So the question is the velocity constant? What do you think as a class? Do we believe that the velocity is constant or not? What do you think? Yeah, Dak.
I think it's constant
Okay. Why would you say that?
because like once it speeds up, the line stays the same.
It's a straight line.
Yeah.
Okay. Anybody else have some thoughts about that? If I'm asking, it's because it's not that trivial, right? Like, so if the first thing that comes to your mind is like, yes, it's constant, because then like hold your breath for a second, think a little bit deeper, because otherwise I wouldn't have. I mean, I would say, yeah, you're right. Like, let's move on. Can we make an argument that in fact Casper's speed is not constant? Is what I'm trying to say. And how do we make that argument? Yeah, Ian.
Well, his coffee filters obviously moved a lot, and it's kind of like what I feel like if it's not like going straight down, or if it's moving left to right, then there's other forces acting on it, not just the forces going down and going up, which would make it, same velocity. But there's a lot of movement, as I can see from his graph and from the picture of the veneer. It's very like, it did a lot of movement, and that's not very constant because that means it's changing speeds going different directions. So it's not exactly the most constant thing in the world. But I feel like these coffee filters could be constant and they cannot be constant, because sometimes it just depends on like the wind in the room, or it depends on like what happens or how you drop it, because it could just fall straight down. You never know.
Mhm.
But it also could do what Casper's did and just go everywhere.
Got
Or
it.
not, but
Yeah. Does that make sense, the argument that Ian just made for everybody? Does that make sense that, right, if you just look at the blue data, it looks like it looks like the velocity is constant-ish. But once you look at the red data, it is going side to side, meaning that the direction is changing. If the direction changes, then the velocity is not constant. Question is, does it matter? Do we care? Right? Like that's another completely valid question, right? But that's an interesting thing for us to think about, like as we're looking at this a little more carefully. All of you, have you had experience where your filters were going side to side? And did you try to address that? And how did you address it? Were you successful in addressing it? Yeah, Leila.
Some of my filters were a little bit like crushed because part of it was folded over because it was in my bag. So when I tried to drop those, it would fell pretty unsteadily. But once I kind of smoothed it out and used the other ones that weren't as crushed and kept their shape more, then it was less so like that.
Okay. So smoothing out your coffee filters before you drop them helps. Anything else that anything else that anybody found as a strategy for making the coffee filters fall more straight down? The deck.
Like turning off any fan that's in the room.
Okay. Yeah, that's sensitive, right? So like if you have a fan, closing windows, dropping, you know, not stopping the fans. Did anybody try to play with the number of coffee filters that you're dropping? Yeah, Leila.
Kind of before I decided on how many to drop, I was just playing around with dropping like 13 or just dropping 1. And I think when you drop less, it's more likely to move side to side.
So more coffee filters, if it's a little bit heavier, right? If it's a little bit heavier, it will also be a little bit more rigid and it's less likely to move side to side. So that's something that, again, like if you want, now that you've got some data, right? If you want to improve your data, one thing you can do is you can like change the number of coffee filters you're using. Again, nobody says you have to use a certain number of coffee filters, right? You can use however many coffee filters you want. More coffee filters tend to give you cleaner data. Okay, so that's room 3. What about room 4? Noel, Mark, and Dak.
Well, we observed that the coffee filter wavered just a tiny bit, nothing too crazy, and that after like once it's sped up in the beginning and then it reached a constant velocity until it hit the floor.
Because of that, we assume that if there are no crinkles or like extenuating circumstances, the velocity would probably be constant because it was almost constant. It was like almost constant in all of our tests.
Okay. Mark, anything to add?
Well, we got a weight of 0.2 newtons,
Okay.
which is slightly more than some other groups. We may have rounded differently. We may have inaccurately measured. But either way, I think we're around the right area. And also for some reason, Noel's graph measured in both X and Y for one line, but Dakota and I's graphs each measured X and Y separately.
Oh, no, I just took one of them out. I took the red one out.
Yeah.
Oh.
So that's an option, right? Under Vernier, you can decide how many graphs you're going to represent on the same, right, on the same graph, and so you can make the decision to represent the X motion or not. Again, notice that some of you, your units are in pixels. If you're doing that, that's probably because you did not put a scale on your experiment. Remember at the beginning of your experiment, you're supposed to put a scale so that the camera knows like how big the world is. But notice that like the red line for both Dakota and for Mark seems to indicate that there's fairly little, if any, side-to-side motion. So the motion is really pretty much almost straight down, which is cool. Nice job. Okay, and last but not least, Leah, Marlo, and Gio.
Okay, so here my teammates and I all like compared our data and we got basically the same thing. So like there's like 3 statements on the bottom left corner. We found that it took about 0.8 seconds for the 5 filters to reach the ground from a height of 5 feet. And that it also traveled at a constant velocity, which we see in the graphs.
Marlo, Gio, anything you want to add? Somebody comment on that sentence, the filters travel at a constant velocity as proved by the linear graph shown above. Can we refine that statement based on all the conversations we've had on the previous rooms? I don't know, let's look at the upper, I don't know, let's look at this data for here, like this data right there. Does that data indicate that the puff filters are traveling at a constant velocity?
Well, at the beginning of like the coffee filter's descent, it is mostly like slower just because like it takes a while to reach its terminal velocity.
Okay. But you can, so you see how you can make a more nuanced statement, right? The coffee filters speed up and eventually reach the state where they're falling at a constant velocity. That would be a much more interesting statement than this traveling, right? Because they're not traveling at constant velocity. Cool. Excellent. Good work. So any questions about this? Any questions about so far anything that's unclear? Like you're going to have to write about this. We just made some comments about the various experiments. Any questions, any comments, anything that you're uncertain about, anything you want to clarify? Once and twice. So I would say make sure that when you put your graphs, make sure your graphs are labeled, right? So here it's really in the graphs on this slide, all the graphs have like time and y, right? Make sure that your graphs have labels on them so that we know what we're looking at. If you don't have any unit or if you have pixels, make sure you put a scale on your graph so that we know how big things are. I left you guys to play around with whatever unit you wanted. What unit should we have, ideally? Time should be in what? Yeah, Liv?
Seconds.
Yeah, time should be in seconds. And X and Y should be in what, ideally? Yeah, Ruby?
Inches or centimeters?
Yeah, in a perfect world, it would be in meters, right? In a perfect world, it would be in meters. In an imperfect world, it would be in centimeters. And in a really weird out American world, it would be in inches. But that's really like, that's a flawed, it's a flawed way of thinking about the world. Okay, so